Okay, let's go ahead and get started. Last week of the quarter, our question of the day involved colors, which I thought was interesting for 143. Blue won out. Blue is actually my favorite color. Maybe it's a lot of people's favorite colors, and I happen to be wearing a blue shirt today, so I don't know whether I didn't do that on purpose. Maybe that was some kind of coincidence. Let me mention a few things before we go into the content for today. So I had mentioned that on Friday last week I posted the resources for the final exam. On Monday I posted the final exam itself. So you can see the structure of the test here, lots of resources like we had before, and then the actual final. Now what I've suggested is that you finish the Huffman assignment first. It's due Friday with a cutoff on Sunday, and that's a hard cutoff, so you have to finish it by Sunday night. So finish the Huffman assignment first. Then, I assume that you're doing at least some thinking about the final, studying for the final. We've been using some of the section time to review things like collections and linked lists to help you get ready. And tomorrow the TAs will be doing their own review for the final, so that'll be another opportunity. Friday, I'm going to do a review for the final. Not going to do a lot other than kind of going through the different questions and mentioning some of the issues that come up. So I've released the final in case there are people who need to take it early, but I would hope that most of you are going to take it after Friday's lecture. You're going to finish up the Huffman assignment first, and then do some studying for the final, and then find some time to take the final. And we want you to turn it in by next Tuesday. That's not a hard deadline, but you should make arrangements with your TA if you want to turn it in after Tuesday. We can accommodate some number of students who would turn it in after Tuesday. If you have kind of a tough final exam schedule or something like that, talk to your TA to make sure it's going to be okay to turn it in a little bit later than Tuesday. But the default then is Tuesday at the end of the day for submitting the final, and we hope that most of you then will do that. And then you'll set up a time to meet with your TA for 15 minutes to discuss how you did and any other questions as you're leaving 143. And then that's worth 20 points. The midterm version of this was worth 10. The final is longer, so it's worth 20 points for you to take the test and meet with your TA. Okay, so that is the information about the exam. And as I said, on Friday, I'm going to talk a little bit about the exam itself and say a little bit about life after 143. Let's switch. So let me go to the document camera. So, and let me make sure I'm looking at the same thing that you're looking at. So the lecture that I'm going to give today is I'm going to talk about something that's known as hashing. I had mentioned that what we're trying to do in the 143 class is to kind of give you the best of object-oriented programming and the best of CS, and we don't quite do justice to either. Last Friday, I gave you kind of the final lecture that involved object-oriented programming, and it was clear, particularly from what we did at the very end, that there are a lot of details that we didn't end up teaching you. There's kind of more to understand than what we had time to cover, but I hope that Friday's lecture gave you a bit of a peek ahead. I think this lecture might also give you a bit of a peek ahead, that there are more things to understand than we've had time to cover. We've covered kind of some basic data structures, but there's still more to do. I'll talk about that a little more in Friday's lecture when I talk about other courses you could take after this course. When I first gave this lecture on hashing, I got some curious comments from students on the evals that they would say, well, I wish Stuart had really explained hashing instead of what he did tell us about. And so I'm puzzled over that. I mean, I suspect that the idea is so simple, this hashing idea is so simple and elegant that they thought I hadn't explained it when I really did. So what I did, to kind of try to bridge the gap for that is that I gave myself an hour to write a hash implementation of a set, and I allowed myself to write up to a page of code. So I'm going to show it to you at the end that I have a one-page bit of code that implements the ideas that I'm going to be talking to you about today. And I have a little client program that we can run so we can see how well it behaves against some of the built-in data structures. So anyway, that's a way to try to convince you that I really am, what I'm going to be explaining to you really is how hashing works. Before I get there, I wanted to do something else, which is kind of to prep us for it. Well, and this is also something that in the olden days when we had more time to do computer science, this would have been something that we would have spent more time on. That I mentioned an idea, I think in the last lecture actually, the idea that there are often trade-offs in software engineering. And so one of the kind of the way of thinking about data structures, I think, is that different data structures have different strengths and weaknesses. And if we'd had more time, we would have kind of spent more time trying to practice, well, if this was the problem you wanted to solve, which of the data structures that we've looked at would you use? So we've taught you the fundamental data structures, but we haven't had time to explore a lot, kind of having you practice that. Well, I wanted to do a specific one with you, which is that I'm imagining that I have an application where these three things are the things that I want to do a lot. An add command that adds something to a structure, a find command, that contains, to see if something is in a structure, and a remove command that would remove it from the structure. And if it's you could imagine this being a set version where it's just individual values, or it could be kind of a map version where you're using a key and there's some data that's associated with that key. So add, find, and remove are the three things that I'm interested in. And these are some different structures that we've discussed this quarter, and I wanted to spend a little bit of time going through them to think about how well they would perform on these three operations. This is, again, one of those days where it's really unfortunate not to have an audience because I get such interesting comments from students about these different structures. It is kind of clear this is not an easy question for people to answer necessarily, which tells me it would have been good for us to have had more practice. You're kind of still learning this, still kind of trying to digest it. But so let's do this example. So the unsorted array would be something like our array int list, although I'm thinking of something that's even more relaxed than the array int list. In the case of the array int list, things could be inserted into the structure in any order, but we preserved that order so that if the client added things in a particular order, we kept things in that particular order. I'm imagining something even more relaxed where we don't care at all the order in which they appear in the array. So we're not maintaining some sequence or something. They can be in any order whatsoever. So how much work does it take? Well, time is what I'm interested in. And you may remember we talked about the complexity idea using the big O notation. So the add command is O of what is kind of the question that I have in mind. Well, how hard is it to add something to an unsorted list? I mean, you may remember that we had 2 lines of code for the array int lists add, where we put something at element data of size, and we did size plus plus. You can just put something at the end of the structure. And so it doesn't matter how many things are in the structure. It's very easy to add to the structure. So remember that what this big O notation tells you is how this is going to vary with the input size. And we'd say it's constant time. It doesn't depend upon, if there are 10 things in the list or if there are 10,000 things in the list. It's going to take the same amount of time to do an add. Now you might object. We had the issue that sometimes you ran out of room and you had to make a bigger array. But I mentioned at the time that we saw this kind of the resizing code for the array int list, that what you do is something like doubling the size. So that particular add ends up being very expensive. But then we can do kind of, so suppose there were 10,000 things in the list and we needed to double the size of the array, we'd be making an array 20,000 long and copying 10,000 things over, which would be very expensive. But then we have 9,999 adds that we can do where we don't have to do that. And so if we spread the cost, amortize the cost across those 10,000 adds, it's still a constant time. That one add is a blip, that it's expensive, but if we average it out over the things that follow, we would say this is a constant time. How about a find operation for a list like this? Well, it's not in any particular order, so that means we've got to look at everything. You may remember that the original version of index of in the array int list class started in an index variable at 0, and it just said, is it at 0, is it 1, is it at 2, is it at 3? It just looked at everything. And if you're doing a find, maybe you get lucky and you find it early, that's possible. If it's not there, you'd have to examine all n things in the list, to verify that it's not there. If there's one occurrence of it, you'd find it about halfway on average. In any event, we describe that as an O of n. It kind of varies with, with the n, the number of things in the list. If we made the list 10 times bigger, we'd expect that it would take about 10 times as long to do a find operation. And then there's kind of remove. I almost feel like adding a fourth column to this, which would be remove after find, because it's an interesting problem to think about. If you knew where the value was that you wanted to remove, typically it's somewhere in the middle of this array. If you knew exactly where it was, the thing is, there's going to be a gap in our list. And normally you'd have to kind of scooch things over, you'd have to shift things down. But if this is a truly unsorted array where things can be in any order whatsoever, is there something better you could do? So we get some different suggestions. I normally get someone who recognizes you could take the thing at the end of the list and put it there where the thing is that you're removing. You could kind of fill in the gap by taking the thing that's at the end and inserting it there in the middle. So a remove after a find would be something you could do very quickly with an unsorted array, but that's not the operation I asked for. I asked for remove, and that involves a find. So this is O of n, that it takes, you're gonna have to do that find operation. And even though you can quickly kind of fill in the gap and decrement the size, it's still got that find operation, which is expensive. All right, what if we decide to have an array, but we're going to keep it in sorted order? Then where do we get an improvement? And people tend to remember that find, is where we can have an improvement. We can do the binary search. We talked about binary search and even wrote the code for it. That one then becomes O of log n. We know that the binary search is log n. So find becomes a pretty quick operation. But now let's think about the others. What about add? Well, you can quickly find where to add. In fact, we wrote our binary search, if you may remember, so that it returned an index that let you know where this thing would belong in the list if you wanted to have it in the list. So adding something, finding where to add is very quick, but then we're going to have to shift things over because it's an array. And on average, we'd shift half of the array. So we don't care about the half, the fact that it's a half. What we care is that, there's an n in there, so that if there's 10 times as many things, then there's 10 times as much shifting, and it takes 10 times as long. Remove is similar, that we can very quickly find where the thing is if it's there, but then we don't want to leave a gap. We can't do the trick that we did here. We can't kind of take the thing from the end and put it in the middle there, or stick it at the end. Basically, the remove requires the shifting as well. So this is going to be an O of n operation as well. All right, how about an unsorted linked list? So this was like our version of linked int list, where we're not keeping it in any particular order. We just have a list of values. Well, what about add? I mean, we saw this many times with the linked list, that adding is very quick. If you have a reference to the front of the list, then you can add immediately at the front. I showed you a version on Friday where I kept a reference to the back of the list as well. So even adding at the back of the list is something that you can do immediately. You can immediately go to the front, immediately go to the back. And then with linked lists, you just rearrange the links. And so this becomes O of 1. Adding to an unsorted list is something that we can do right away. What about find? So find is, it's a similar kind of thing where we start at the beginning. How do you find things in a list? You see if it's the first thing, and if not, you go next, 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 next. You go through the whole sequence of things, seeing if you see it there. If it's not there at all, you're going to have to look at all n things. If it occurs once, you're going to look at half of the n things. So this is very similar to what we had with the unsorted array, that it's going to take O of n amount of time to do that. Remove after a find would be very quick, because if we kept track of where we were in the linked list, rearranging links to remove something is very fast. We don't have to do the shifting that we had to do for arrays. So if I had that fourth column where I said, kind of remove after a find, that could be very quick. That could be O of 1, but this one does require the find, so it's O of n. It's going to have to find it first before it removes it. Well, how about a sorted linked list? Does this improve the speed? Now, with the sorted array, we were able to do binary search. But for a linked list, remember that the way binary search worked was that the action was always at the middle. We were kind of looking at the middle value and seeing what was going on there. How do we get to the middle of a linked list? Well, we got to start at the beginning and go next, 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 next. I mean, I showed you a version on Friday that had where the links went in both directions. So it was a doubly linked list, and we kept track of the end of the list. So you could start at the front and go next, 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 or start at the end and go prev, prev, prev. But actually, the middle is the one that takes a long time to get to. So we're not going to be able to do a fast binary search, because looking at the value in the middle takes a lot of time. We have to go through all of the values, either from the beginning up to the middle or from the end down to the middle. So find ends up being an O of n operation. It can sometimes be a little bit faster in the sense that if you have a sorted list, like suppose you were searching for a 42 in the list, and you start looking at values starting at the beginning, and you see a sequence of values. If you came across a 50, for example, and it's a sorted list, well, then then you could stop, because 50 is bigger than the 42, so if you haven't seen it yet, you're not going to see it. So you might be able to end a little bit early, because it's sorted. It might not take quite as long as the unsorted version takes, but typically that would maybe lead it to take half as many comparisons, because you can end the search early. But you still have to do a lot of searching, and you can imagine scenarios where it has to look at every single thing. If it's a value, for example, that's bigger than everything in the list and it's not there, then you'd have to look at the whole thing, at all n things. So O of n for that. Adding now is going to be expensive. This is one where if you knew where to add, then it wouldn't be so expensive. So add after a find would not be expensive, but add requires the find. So it's going to have an O of n. And it's the same thing here, that if I had that fourth column, remove after a find would be very quick, because it's a linked list, but it does have the find. It requires the find. So that's going to be O of n. So sorted linked list, O of n, O of n, O of n. That's like the worst of all these different things. It's kind of the worst choice in terms of performance on this particular combination of three things. Well, what about a binary search tree? We have to talk a little bit about that. What did we do when we were building up a tree? You may remember that, I gave you an example where we were inserting names, and so the first name inserted became the top of the tree, and then we might add something over here, add something over here, add something over here, maybe we add something here, we add something here. And so we didn't really talk about how much work is involved in doing these various things. So let's talk about that now. Well, so when we did the add command, what did we do? So when we had a new name that we were going to add, we basically said, is that name alphabetically less or alphabetically greater than the one that's here? And so we would say, suppose it was greater, then we went to the right, and then maybe it was alphabetically less, and so we went to the left, and then maybe it's alphabetically greater, so we would know it belongs over here, and there we found the spot that we wanted to insert it. So an add involved descending the tree, kind of going left or right based on whether it's less than or equal to or greater than, until you get to a spot to insert it, and then where there's an empty branch, and then we would change that empty branch to a leaf. So that was kind of the way that we solved this problem. What that means is that the amount of time required for an add is going to be related to the height of the tree, the number of levels of the tree. Because it's this descending task until we get to some spot. So an add command is going to be related to the height. How about a find command? We didn't write a contains method, but we could use the exact same trick, is that we know that we either go left or we go right depending upon whether it's alphabetically greater than or alphabetically less than or equal to, and maybe we actually find the value, in which case we could return a true. So it's a descending task, just like the add command is a descending task. So it's related to the height. Well, what's the height of a tree? It kind of depends upon the structure of the tree. What we'd like is to have a tree that does lots of branching. When you do that, because trees, you have one node at this level of the tree, but there's potentially two nodes at this level of the tree. Here, there's spots for 4 values at that level of the tree. And then there would be a space for 8 things at this level of the tree. So we double the number of nodes in our tree every time we go up by 1, which is really good. So if we could assume that we had what we would call a balanced tree, where it's mostly full, if that was kind of what we knew was true. So suppose that there are n nodes in this tree, then what's the height going to be? Well, basically, those n nodes would be 2 to the height, because we're doubling the number of nodes at every single level. Every time we add 1 more to the height, we have twice as many nodes as we had before, which means that the height is going to be on the order of the log to the base 2 of n. It's going to be around log to the base 2 of n, assuming it's a balanced tree. I'll say more about that in a second. But if we have a balanced tree, then we know that the height's going to be around the log to the base 2 of n, and then add and find are going to become log n operations. I've mentioned this several times now, but I often use this little approximation that 2 to the 10th is around 10 cubed. So if you were thinking about if you put 1,000 things into your tree, and it's a balanced tree, it would have around 10 levels to it. If you put 1,000,000 things in your tree, it would have around 20 levels. If you put 1 billion things into your tree, around 30 levels. If you put 1 trillion things into your tree, it would be around 40 levels. So, 40 that's a tall tree, but 40 is still, if there's 40 operations to be performed as it descends the tree, your computer can do 40 things pretty quickly. So this was for the add and the find, that the add would be O of log n, assuming a balanced tree. The find would be O of log n, assuming a balanced tree. Remove is an interesting case that if we wanted to remove something from a binary tree, we haven't really talked about this. Maybe let me throw in one more node here just to have an extra little example in this particular tree. But suppose that we wanted to remove something. We used to devote an entire lecture to writing the code to remove from a binary search tree, because it's an interesting task. Suppose you discover that this is the value that you want to remove from the tree. What you have to do is to select something from some node to replace this node, to restructure the tree. And if we'd had time to talk about it, we would have mentioned the idea that you find them, if there's a left-hand subtree, you find the maximum value in the left-hand subtree, which is this value right here. And so this value can kind of replace the value that's there to rearrange the tree and still have a binary search tree. So again, as I said, in the old days when we had more time to discuss the computer science parts of this, we would have done a whole lecture on removing from a binary tree. But I'm just trying to let you know that it's yet another descending task, that it kind of involves going from the root, to a leaf. And so it's related to the height, that the remove also is going to be an O of log n. Now that's assuming that we had a balanced tree. But are we going to get a balanced tree? You may remember that when we did those names from the TV show Schitt's Creek, the first name that we added was Twyla. And I didn't even notice it at the time. I just I had used this shuffle tool to randomize the sequence of names. But Twyla is the highest, the last name alphabetically. And so it was a very degenerate tree where we had Twyla up here, Twyla, and then everything else was over here, and there was nothing in the right-hand subtree. So there was no branching at all at the very top. But actually we got a pretty good branching from that one that was to the left of Twyla. So, the question would become, how bad could this be? And again, it's nice if I had an audience and I could get you guys to give me suggestions about how bad it could be and what are the cases where it's really bad. This kind of suggests a case where it's bad because it was alphabetically the largest thing. What if you had the names in reverse alphabetical order? Well, then the first one would go here, the next one would be inserted 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 here, off to the left. What if they were in forwards sorted order, so that the first thing in the sequence that, the first thing that you added to the tree was alphabetically the smallest value? Well, then you'd have a degenerate tree that kind of goes off to the right. What you'd have in that case is a sorted linked list which had the worst performance of all. So the binary search tree, if it's not a balanced tree, can become this, terrible sorted linked list. So, it's odd that the thing that it does so badly with is data that's already sorted. So it's kind of unfortunate. There's a weird thing that you can sometimes do. If you knew that you're writing code like we're writing, where we're not doing something special to make sure the tree is balanced, it can be helpful before you build up the tree to actually randomize the sequence of values that you're working with, to shuffle the values that you're working with, because then it's unlikely that you're going to end up with something in forward sorted order or reverse sorted order, or even if you have, say, one of these values that's not very good at branching, you're not likely to have 2 of them, 3 of them, 4 of them, 5 of them. You're likely to have, say, just one value that's kind of not very good, and then you start getting a better value. So it's a weird case where before you put things into sorted order, it might be helpful to randomize them, to shuffle them beforehand. But there's much better techniques than that. There are a lot of different ways of having a balanced tree. Some of them guarantee that you'll have a balanced tree. Others are probabilistic in the sense that they basically, they're not guaranteed to produce a balanced tree, but it's highly likely that you'll end up with a balanced tree. If you continue after this course by taking the non-majors 373 course or taking the majors 332 course, those courses tend to pick up where this one leaves off. They tend to say, well, you studied binary search trees in 143. Now let's talk about how to have balanced binary search trees. So we don't have time to do it in this course, but I'm kind of letting you know that of course we want to have a balanced tree, and that's what you would study at the beginning of 373 or 332. As I said, I'll say a little more about that in Friday's lecture when I talk about kind of courses that come after 143. So, I guess what I would say is that looking at these different values, binary search tree looks pretty appealing. It's log n, log n, log n, so, all of them are well contained. Remember, if you have 1 trillion values, then it's 40, 40, 40, 40 levels to the tree. Oh, let me mention, by the way, there's another thing that I wanted to say about that just reminded me, talking about the number of levels of the tree. We know that you want to be careful when you write recursive code that you're not going to have the recursion go too deep. You might be dealing with that in the Huffman assignment. You might have code that works for short.txt but not for hamlet.txt. So we want to be careful to kind of, if we're going to write recursive code for binary trees, we want to have some guarantee that it's a limited number of levels. So that's kind of another reason to want to have the balanced tree. That's why they're willing to write recursive code in the Java class libraries, because they know that they're going to have a balanced tree. So they're not going to end up with the kind of problem where they have recursion that goes too deep. So that's pretty good. Binary search tree, pretty nice answer for these things. Much better than the other ones here on balance. There is a limitation of the binary search tree. I'm going to say more about this on Friday as well, because it's part of the review for the final. But not everything can be put into a binary search tree. The binary search tree involves putting things into sorted order. So what kind of data? Well, that would be the data that implements the comparable interface. But not everything implements the comparable interface. And so, there are some data for which we just wouldn't be able to use a binary search tree. So that's certainly a limitation that we want to be aware of. Well, I want to talk to you about something that's known as a hash table. And I've cheated a bit, or trying to make this a little more dramatic than it might seem otherwise, is that I have purposely chosen the three things for which a hash table shines, for which a hash table is particularly good. Remember, it's going to depend upon the application that you're doing. I mean, if you don't do very many of a certain operation, then it may not matter. So I'm assuming here these are the three things that matter, and we're doing them a lot. Well, and it turns out that for a hash table, the answer here is O of 1, O of 1, O of 1. Constant time for all three operations, and it doesn't require that it be data that implements the comparable interface. So if this really was the case, that these are the three operations you're most interested in, and you cared about it running fast, then the hash table would be the thing to choose. So let me explain to you a little bit the idea behind the hash table. The first idea is that there's what we refer to as a hash function. So the idea of the hash function is that given some data, it returns an int. So that it's able to turn data into a simple int. Now, this function is a function that is going to lose some information along the way. So that, this data, we use the data to produce an int, but we can't necessarily go from the int back to the data. I mean, strings, for example, there are a lot more possible string values than there are int values. So it's definitely going to be the case that when you have a hash function for strings, that more than one string is going to end up with the same int value when you do the hash function. So it's not a unique int. It's just that there's some way of doing that as an int. I did something before lecture because I wanted to be able to give you an example. Java decided to include hashing as a central part of the language. So there is a method known as hash code, and hash code is a method that's defined in the object class. So you know that everything derives from object one way or another. So every object in Java has a hash code. So Java was kind of built for hashing. That you can you have a hash function for all of the different data that you're going to have in a Java program. I ran this before. I did this in the interactions pane, and it told me that the hash code for my last name is 788398442 is the hash code for my name. Well, hashing is one of those things where there's a time-space trade-off. So I've mentioned the idea that you can generally make things run faster if you're willing to have them take up more space. And it's done by having what I would describe as a roomy array, an array that's got extra space to it. So suppose that you were going to insert, something like 7,000 values into this structure. Then 7,000 is how many bits of data you're going to have. So maybe you'd make the array be 10,000 long. So you make it bigger than the amount of data that you're going to be inserting. So we're going to have some kind of an array here that for our data. There's a 0th element and a 1 and a 2, etc., down to 9999. 9999. The idea is that we use the hash code as a way to figure out where to put this in the structure. So this int is too big. The array only has 10,000 spots in it. How do you take an int like that and turn it into something that has just 10,000 possibilities? Well, this is another great application of mod. Stuart loves mod. Computer science loves mod. If you mod this thing by 10,000, it'll give you something in the range of 0 to 9999. When you do that, what you get are the last 4 digits, 9842. So what I would do with this is I would go to the location 9842, and I would put Regis in that spot. So let's think about why these operations are as fast as they are. So when I go to add something to the structure, I have to ask for its hash code, but that should be a constant time operation. I have to mod by the size of the array, but that's easy to do. I need to go to that spot and then put the value there. So I can very quickly add something into the structure. If I want to find if something is there, I figure out the hash code of the thing that I'm trying to find. I mod it by the array length because I know that that's what I would have done if it had been added before. I go to that spot and see if it's there, in which case I say, yeah, it's there. Otherwise, I'd say it's not there. And when you go to remove, I say, oh, okay, well, let me ask for its hash code, find the spot in the array where it belongs, go there, and then just undo the add, kind of remove this thing from that spot. All very quick operations. And this is normally when I get people who are kind of like, wait, it can't be that simple. And that's true, it's not that simple, that we can have what's known as a collision. So you might have more than one string whose hash code is this. In fact, it's a whole lot worse than that. You might have a string whose hash code ends in 9842. A whole bunch of strings are going to have a hash code that ends in 9842. So that means that if you inserted a bunch of them, they'd all end up at this spot, the 9842. So there could potentially be more than one thing here in this particular spot. So how do we deal with that? How do we make it possible to have more than one thing at that spot in the array? I get different suggestions from people. For some reason, people like to think about 2D arrays, maybe because we just talked about 2D arrays. That's really expensive. A part of the problem is you don't know how big to make the 2D array, how many columns to have. Are you going to have 3 extra things, 18 extra things? You want something flexible here. So it's all sorts of things people suggest. But the thing that I kind of like it when I hear it is that people say, well, couldn't we have a linked list? Couldn't we put a linked list of values here? So that way, if I wanted to have none, it's just a null. If I want to have 1, I've got a pointer to a node. If I want to have 3 of them, I got 3 nodes that I link together. This is a technique that's known as separate chaining. And this is what the built-in Java hash set and hash map use, is they use this technique of separate chaining. There's a big roomy array that have references to linked lists. That's how it's done. Now, there's when we talk about hashing, we normally talk about something that we abbreviate as lambda, the load factor. I mentioned that we want a roomy array. Typical values for lambda would be something like 0.75. That we kind of don't want things to be more than 75% full. What the built-in structures do is that if this ever gets more full than the 75%, then we create a brand new array that's bigger than the original, and we rehash everything, kind of move everything over to make sure that it stays in that nice, roomy form. So I didn't mean to imply that hashing is trivial. Hashing there's a lot of really interesting, rich theory for hashing, and I would say that it centers around what kind of hash function to use and what kind of collision resolution strategy to use. This, a separate chaining is just one collision resolution strategy. There are many collision resolution strategies, and you would study that more if you go on to take the 373 or the 332. So they'll talk about other collision resolution strategies that you might use. So there is a lot of theory. I mean, there's a lot to know about hashing, and we've only scratched the surface. But I have given you the basic idea. The idea of turning something into an int, finding a spot in the array, and then adding it. If the hash function does a good job of spreading the values out in the full range of int, and you have a good collision resolution strategy, hashing tends to work well. I mean, everything can fall apart in a worst case scenario, but it's highly unlikely that hashing will fall apart if you have a good hash function, a good collision resolution strategy. Let me give you an example of a bad hash function. What if your hash function was just return 42? Everything goes at spot 42. Or let me give you another one. You're working with character values, ASCII values. Imagine that for a string, I kind of just added up all their ASCII values, just the sequence of values, plus. I added them all up. Well, words are something like 20 characters long, and, these hash values, these character values you've seen are kind of go up to maybe 100. So if you had things that were 20 long and, each individual value was maybe 100, then the sum of those 20 values is going to be something like in the range of 0 to 2,000. That's not a good hash function. That only spreads it out among 2,000 possibilities. That means that everything's going to cluster in the top of your array here, in the top 2,000 entries. What the built-in string function tends to do is something more like adding up the character values like this, as if you had shifted it by multiplying, by 100 or something like that. So you add up something like this so that you get a much wider range of possibilities. So it does matter that you use a good hash function. It does matter whether you're using a good collision resolution strategy. But otherwise, those are the basic ideas. Let me switch to the computer. So let me bring up the laptop, send it to the projector. Make sure I'm looking at the same thing that you're looking at. And let's take a peek over here. So I have a program called HashTest that's some client code that's going to allow us to run a program. It's a silly program. It doesn't do anything really useful. It just has a whole lot of calls on add, find, and remove, kind of that combination of three things. Here's the one page of code that I ended up writing, to use the ideas that I was just describing to you on that pad of paper. So I'm going to make linked lists. So since I'm making linked lists, you'll see that there's a node class. And what I have in there is some data. I want to have this be generic, so it's it's of type object, and a reference to the next node. So I've got a private node class. I mentioned in Friday's lecture that that's the typical thing to do. And then I've got these different methods here. So I have an index of method that it asks for the hash code, like I was saying, if I asked for Regis hash code, and then I mod it by the length of the array, and I use an absolute value because I don't want any negatives. So what I do here, so let's take a look, for example, at the contains method. So if you wanted to know whether this thing contains a value e, it first does that computation of figuring out, well, what would the hash code be, and then what happens when you mod it by the array size, and that gets me a specific index into the array. And so that's going to be a reference to a linked list. This is an array of linked lists, an array of references to the front of a linked list. So I kind of take the ith entry in that array, and then this is just typical linked list code. I set a current to be that. While the current is not null, I see whether I found it, and if not, I set current to current.next. So contains kind of works that way. This is, remove does the same kind of thing where it figures out, where this would be. And if it's there, it writes the typical kind of linked list code to remove something from a linked list. You do something different when it's the front of the list versus changing a dot next. So this is changing a front and this is changing a dot next. But otherwise, this is just basic linked list code. I'm going to throw something in here to try to prove to you that I'm being honest. I usually ask the class for give me some phrase that you would recognize. How about if I throw in Biden as a phrase, just to kind of show you that when I run this later, that it's going to be our program that's running. So I have this hash test program that I can run. So let me run it once. Oops, I don't know why it wants me to recompile, but let's recompile. And I'm going to give it Moby Dick, and I'm going to tell it to use the array list. Now, what I did for the array list is the unsorted list. As I kind of just had everything in there, but there's no sortedness. I use that technique I mentioned where I kind of fill in the gap by moving the thing at the end to the beginning. It's not a good way of doing things, and you can see it's taking a while to kind of process this. It took 18.795 seconds using just an array list. Well, let's see how it improves the Moby Dick file when we do tree set. So this is a binary search tree, 0.187. That's a whole lot better. That's like 100 times faster than what we had with the array list, because it's O of n, O of n, O of log n, O of log n, O of log n for those different operations. But let's try running with Moby Dick and the built-in hash set that Java gives. So 0.187 is what it took when we were doing the tree version of it. This one takes 0.076. So it's more than twice as fast, the built-in hash set. Let's try it again, moby.txt, and let's use our hash set. So we should see Biden printing out if it's constructing our hash set. There's the Biden, just to kind of prove to you. So ours took 0.081, so it's a little slower than the built-in hash set, but more than twice as fast as the built-in tree set. Think about that for a second. They have had decades to make tree set run super fast. I spent an hour writing a hash set that is running more than twice as fast as their very sophisticated tree set. That's our one page of code there that's running that fast. So, picking the right data structure for the application, knowing the right data structure to use, turns out to be very important. Let me just show you one more. I'm going to do all.txt, and let's do it with the tree set. This is a file that I made by getting all of the scripts for Star Trek Next Generation, all 7 seasons worth of scripts, and making a great big text file out of it. When I tried to open it in JGrasp, it crashed JGrasp. Somebody asked me to include it on the calendar. I'm going to include it on the calendar, but open it at your own risk. It's a gigantic file. But if you want to kind of run this on your own. So it took 1.284 seconds, still very fast, even though it's a gigantic file. What is that? That is 1,802,000 words. That's a lot of words to be working with. Let's run it all.txt with Java's hash set. So it was 1.284 for the tree set, 0.433. So almost 3 times faster for the built-in tree set. And if we do all.txt with our version, we'll see Biden being printed out here. Ours ran in 0.399. We beat the built-in hash set. It actually often comes close to the built-in hash set. Now, it does some extra things that mine doesn't do, like resizing. So, take that with a grain of salt. But we have something that's competitive with the built-in structure. Let me show you something briefly. I'll show it to you more in Friday's lecture, because I did want to talk about this idea of things that you might want to do after the course. I am going to open a file So in my 143 directory, I have something called SRC, which is the Java source code. And I want to look at the string class. So it's in a package called java.lang. And the string class, I can open it up here. I did this before lecture to take a look. The built-in string class, this is its hash code, if you want to kind of see how it's done. It's not doing times 100 that I mentioned, it's kind of doing times 31. But I'll say more on Friday, that you can look at the Java source code if you're interested. So anyway, I'll leave it there. We'll talk more about it on Friday, that this is a kind of a fun thing to do if you're interested in seeing